Okay, so welcome back to the lecture series of group theory. In the last session, we discussed the definition of group and various examples of groups. Um, some very familiar examples of well-known number systems and under the usual operations of addition and multiplication. And we saw some one or two some non-technical, non-familiar examples also. For example, the matrix group of matrices, the group of general linear group, the group of matrices under multiplication, which are non-singular matrices. And at the end, we saw an example in which we have the nth roots of unity of a complex number as a complex number. Now, in this session, we are going to describe the elementary properties of groups, in which the first of these properties is the uniqueness of the identity. So, in theorem 2.1, uniqueness of identity, we want to say that in a group G, there is one and only one identity element. There cannot be more than one identity element. So, as you recall from set theory and logic, whenever we want to prove this statement that there is a unique element which satisfies some property, we always have to go contrary to the statement. Like, first, let me tell you what is the statement say. What does the statement say here? This statement is about the existential unique quantifier. So there is only one, as you remember from the logic, that we are talking about the existential unique quantifier. So there is only one identity element. Now, to prove this statement, we will assume that, contrary to this statement, that there are more than one identity elements. There are two identity elements in a group. So suppose E and E prime both are identities of G, and as E is the identity, so it will satisfy that property of the identity, that if it is multiplied with any element A, then it gives back A as the product. So AE is equal to A for all AE, A in G. And similarly, if I consider E prime as the identity of the element of the group G, then it will satisfy again the same property. Like E prime when multiplied with A again gives me A for all A in G. Now, if I take these two equations, in the first equation, as this equation holds for all A, for every element A in the group. So in particular, I can take also A is equal to E, right? So in particular, if we take A is equal to E prime, then this equation becomes um, E prime E is equal to E prime. What I have just done is replace this A, which was any element in G, by E prime, which we have assumed to be the identity of G. So I have replaced A with E prime on both sides of this equation. Similarly, if I replace A with E in the second equation, so in 2, if I replace A with E, then this equation becomes E prime E is equal to E, right? And if I compare these two equations, I can see the left hand side are both equal, and this implies that E prime E is equal to E prime, as well as is equal to E from first and second equation. So from first equation, I get E prime E is equal to E prime. And from second equation, I get E prime E is equal to E. So from both of these equations, I get E prime E is equal to E prime is equal to E. This means this is a contradiction to our assumption. We assume that we have two distinct identity elements, but here the contradiction says that we have those two identity elements are in fact the same. Thus, here we have shown that the identity is unique. So there are not more than one identity element in any group G. So this is the proof of the first property.